In the next example, we're looking to find the point P on the line y equals 3x that is closest to the point 50, 0. What is the least distance? Prove your assertions analytically, and they give us a hint here about using d equals d squared as the objective function. Okay. So, a quick little sketch I can draw here for the situation. I can draw y equals 3x, so it's, goes to the origin, but it's relatively steep. And 50, 0 is going to be way over here. And so I want to figure out which point is closest. So I know that if I go straight to the left or straight up, that's not going to be as effective as some sort of diagonal distance. So that's what we're looking for, is some sort of diagonal distance to that point. All right, now how to find that diagonal distance. So I'm trying to find an ordered pair on this line, and so the distance between 2 points can be computed with the distance function. That's going to be my part of my objective. So as I get to my objective for distance, we know that distance is, the distance formula is, I'm going to fill in a couple things here, but the general distance formula would be x2 minus x1 squared plus y2 minus y1 squared. Something like that is the distance formula, and again, whatever you call those things in there varies depending on what resource you're looking it up. But I'm just subtracting the two x coordinates, squaring it, subtracting the two y coordinates, and squaring it. Okay, so we're going to start modifying that with some constraints. The first thing that I would probably put in there before I even talk about constraints is that this point right here is specifically 50, 0. So I'm not looking for any ordered pair. I'm looking for specifically comparing this to 50, 0. So we're going to put 50, 0 in there for x1 and y1. So that changes this to d equals square root of, since I don't have x1 and x2 anymore, let's drop the subscripts and just call this x. So x minus 50 squared plus, and then y squared, because I'm subtracting 0. Okay, it looks a little better already. We don't want to take derivatives and have to worry about subscripts while we're going through, so we're going to just change those variables from the original formula. Now, this is still in too many variables, so we are going to need a constraint. And I'm going to write my constraint function over here, and then in step 4, just keep on going down the line as I sub it in. So my constraint is that this point is not just any old point, it's a point on this line. So my constraint is simply that y is equal to 3x. So I'm going to plug that in for y here. So d is equal to the square root of, this is technically step 4 as I begin subbing the constraint into the objective. So this is square root of x minus 50 squared plus, and then 3x quantity squared. Now, I'm going to eventually take the derivative of this when I get to step 6. Take the derivative of this square root as it is. I'm going to have to chain rule it. So I'm going to have a 1/2 power, all that to the negative 1/2 power, and then the derivative of the inside. It's going to be a pretty messy derivative. The hint is just to square both sides and use a capital D for the square of distance instead. Because that distance is always going to be positive, its square and its square root are going to have minimums at the same place because of the way the numbers line up. If you square a number that is less than another number, its square will still be less than the other number squared. Let me just write that down since that might be hard to visualize what I just said. But if a is less than b, because they're both positive, I know that a squared is less than b squared. So I can look at the square instead, because I just need to guarantee the first condition. The square is going to hold true for positive values. So this is going to work in both ways for positive values. It doesn't work for the negatives, of course, because they are numbered differently, but it's going to work for the positives. So it's okay just to look at the square function, which is very nice because it makes the derivative a lot easier to find. I won't need to use that negative 1/2 power and so on. Okay, so continuing on with this, we need to, in step 5, consider the interval of interest. Okay, so the interval of interest on this one, I think we'll be able to bound it by two numbers, get a nice interval of interest. I don't know where this point is for sure, but at the very least, it is between if I went straight over and if I went straight up, right? It's between those 2 points. So I know that the largest bound I could have on my x value is 50, and the smallest it could be is 0, which would be straight over. So it's not a very good bound, but I do know that 0 is less than or equal to x is less than or equal to 50. That would be the inequality way to write it. Or I could just say x is in the interval 0 to 50 if I wanted to write it in an interval. Either one of those is fine as interval of interest. Now, obviously, it's not going to be one of those two boundaries. It's going to be between them, though, for sure, right? So I do have a bounded interval on that. It's definitely between those two values, which are the straight up and straight over, right? If I'm at 50, 0, I go straight up, I still have an x value of 50, and if I go back to the origin, I have an x value of 0. Okay, so that gives us an interval of interest, and then moving back over here, we're ready to begin computing our first derivative. I may want to simplify this. I probably don't want to expand that, but maybe this part could be expanded. The 3x squared could be expanded pretty quickly, and I'll write it in function notation real quick as well. This is technically part of step 4 still. So d of x as x minus 50 squared, and then just plus 9x squared. Okay. Then in step 6 for the derivative, we'll use the chain rule on the first part. So we'll get 2 times x minus 50 to the first power times 1, and then plus our 18x. Okay, that's step 6 is just the derivative. And then step 7 is where we set the derivative equal to 0 and doesn't exist. It's polynomials. Oops. So there are going to be none of those. So we don't have any places where the derivative fails to exist, but we will have places where it is equal to 0. So 2x minus 50 plus 18x equals 0. That gives us 20x minus 100 equals 0. So that's 20x equals 100, and that gives me x equals 5. I only have one first order critical value here, so we're going to use that. All right, in the next piece, one first order critical value. And then step 8, we get to use any of the tests. Last time I think we used the second derivative test, so just to vary it up and see how all the tests work, we're going to use the test for absolute extrema. So this is part B, the test for absolute extrema. Remember that test from the very first section in this chapter. We're going to evaluate the original function, which is called d here, so d of x at the two endpoints of our interval and at our critical value. So we're going to do d of 0, d of 5, and d of 50. All right. So I'm not evaluating the derivative. This is the original function. So back up here, the original function, if I plug 0 in here, I have to figure out what 50 squared is. So 50 squared would be 2500, so 2,500. Then I'm going to plug in 5. I'm going to use a calculator to do some of this. So I need to plug in 5, and so we have 5 minus 50 squared plus 9 times 25. So that is 2,250, and then we want to plug in 50. Okay, so 50 minus 50 squared, and then 9 times 50 squared. And so we have 22,500. All right. So flipping back to the other screen here, these are the three numbers that we got. And since our goal was to find the least distance, we need to just find the absolute minimum. So out of these two values, On our interval, we have the absolute maximum and we have the absolute minimum, just because they happen to have the smallest y value. The middle one's the minimum, the biggest one had the largest y value. So you can tell from the diagram that that one definitely was the biggest, and this one hopefully is our smallest point, wherever that point happens to be. So our conclusion is going to be, this is not the y-coordinate, of course, this is the distance squared, the distance squared there. So the y-coordinate would be, back up here, y is equal to 3 times x. So as I get into step 9, finishing off conclusions, y is equal to 3 times 5, so 15. And then we might want to find little d as well as the square root of 2,250, which may be simplifiable. I don't know. So let's find out. Okay. So if I take 2250 and we divide it by, I don't know if 25 goes in. It does, 90 times. And 90 is, of course, divisible by 9. So I should get 15 square root of 10 here. Okay, so this will simplify to 15 times the square root of 10, right? Because 225 is 15 squared. There we go. All right. So getting our conclusion, we have the x value was 5, the y value is 15. So 5, 15 is at a least distance of 15 square root of 10. I don't think I have units on here, so units away from 50, 0.